Ladies and gentlemen, welcome. This is our seminar 4ST601 Statistics and the seminar number 5. Today we will continue with correlation analysis. So calculation, the correlation between two variables, variable x and variable y. And after, we will immediately continue with regression analysis, where we will try to explain one variable by another variable. So please make ready your formulas on this page where is correlation and regression analysis. And we can start with first example. I prepared for you another Microsoft Excel sheet where is example 5.1 and we will start with this example. Suppose that we received data from 6 households about the number of members in the household and their monthly expenditures, and the values are, for example, in thousands Norwegian crowns. Yes? So there is a table where we have two variables. Number of members, yes, in the flat, in the house, in the household, yes, and monthly expenditures on the food, on energy, etc. Yeah? So monthly expenditures. And we would like to calculate the correlation coefficient and try to interpret the tightness of this dependence. So we would like to calculate if there is a relation, yes, correlation between number of members and expenditures on this household. Yes, I expect that yes, because logically, if you have more people in the house, yes, you need more money, for example, on electricity, water, food, etc. Yeah? So monthly expenditures are probably higher if you have more persons in the house, yes. But we would like to explain this. So first, we will start with calculation of correlation coefficient, and after we'll calculate the parameters of the regression line that is describing the dependence of the monthly expenditures. Yes, regression line. We will calculate the intercept and the slope. Yes. And after, we will use this model and you will see what we will do. Yes, so we will start with correlation analysis. Okay, so you can see that I rewrite it on the whiteboard the data set. Yes, the series of data, the variable x and the variable y. Yes. And first, what we have to do is to calculate the correlation coefficient, and according to formulas which you have written in your formulas sheet, we have in the numerator there is a multiplication x and y mean minus x mean times y mean. Yeah? So there is a multiplication from variable x and y and calculated mean. Yes, there is a mean from variable x and there is a mean from variable y. Yes, and in denominator there is a square root. Yes, and below this root we have multiplication of two differences. There is difference x squared mean minus x mean squared times, and there is the same but with variable y. So y squared mean minus y mean squared. Yes. So this is the formula of the correlation coefficient. So we need to calculate new columns. Yes, we need to calculate here xe squared yes, another column with second power of the variable x, another column y squared, yes, with second power of variable y, and multiplication xe, ye, multiplication of variable x and variable y. Yes, and when we calculate this, we have everything, yes, and we can use this formula for calculation of correlation coefficient. So the second power of variable x, 1, 4, 9, 16, 25, and finally 36. Yes, this will be maybe a little bit complicated. 6 squared, 36, 8 squared, 64, 12 squared, 144, 15 squared, 225, 22 squared, 484, and finally 23 squared is 529. Yes, so second new column, and now multiplication. 1 times 6 is 6, 2 times 8 is 16, 3 times 12 is 36, 4 times 15, 60, 5 times 22 is 110, and finally 6 times 23 is 138. Yes, so this is what we need for calculation of correlation coefficient. Yes, and now the means. Yes, the mean calculated from variable x, the mean calculated from variable y, the mean calculated from variable x squared, the mean calculated from variable y squared, and the mean calculated from this multiplication. Yes. So I will use calculator and I will solve everything here on the whiteboard. Yes, and in the case of second example, we will use Excel, Microsoft Excel, because in the next example we have larger values, yes, with decimals, and it will be more complicated. Yes, Microsoft Excel is allowed during all our seminars. Yes, so why not? Yes, we will do this. But I will show you everything manually and after in Excel. So the means. Yes, we are in the 5th seminar. Yeah? This is seminar number 5, so you must be able to calculate the mean. Yes, it will be very sad if you will not be able to solve the mean in the 5th seminar. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6 is 3.5. Yes, 3.5 is the first mean. The second mean, 6 plus 8 plus 12 plus 15 plus 22 plus 23 is 86 divided by 6, 14.33. So this is the second mean. And we can continue. 1 plus 4 plus 9 plus 16 plus 25 plus 36 is 91 divided by 6, 15.17. I'm using only 2 decimals, yes? And we can continue. 36 plus 64 plus 144 plus 225 plus 484 plus 529 is 1482 divided by 6, 247. Yes. And finally, this mean calculated from this multiplication. 6 plus 16 plus 36 plus 60 plus 110 plus 138. Result is 366 divided by 6, 61. So again, there is x with stripe, there is y with stripe, there is x squared with stripe, there is y squared with stripe, there is x, y with stripe. Yes? We have everything, and we can use this formula and calculate the correlation coefficient. So, if you remember, the correlation coefficient has in denominator xy mean, so 61 minus the multiplication from mean of variable x, so 3.5 times variable y, 14.33. Yes? So this is the numerator, and in denominator we can find the multiplication of two parentheses. In the first one we have 15.17 minus 3.5 squared. Yes, so this is the mean calculated from second power of x, and that is the mean of x in squares. Yes, and multiplication, and the same for variable y. So 247 minus 14.33 squared. Yes. Okay, so this is in denominator. Now I will calculate r is equal to, in denominator we have this minus 3.5 times 14.33, 10.845. Yeah? So this is the denominator divided by, there is square root, and we have here 15.17 minus 3.5 squared, 2.92 multiplication, 247 minus 14.33 squared, 41.65. Okay, so I will solve this multiplication. 2.92 square root from this value, and finally it's 10.845 divided by the old denominator, and the result r is equal to 0.9834. 9834. So this is the correlation coefficient, the correlation between variable x and variable y, correlation between number of members in the household and monthly expenditures, or correlation between monthly expenditures and number of members. Yes, it doesn't matter the direction, yes, of this dependence, but we must know that this coefficient is element of range -1 and +1. Yes, if this correlation coefficient is close to -1, there is a strong negative correlation, strong negative dependence between two variables. If this coefficient is close to +1, there is a strong positive correlation between these variables. So it means if you have more people in the household, you need more money, yes, for this household, more money on food, on electricity, there is more rubbish, yes, more water necessary, etc. Yes, so there is strong positive correlation. If the correlation coefficient is close to 0, there is no dependence. Yes, but this is not our case. Another very important statistic here. Do you know which one? This one. Yes, in the numerator of correlation coefficient, this is covariance. In the numerator you have covariance. Covariance is a statistic, yes? Covariance here in the numerator is a statistic. Covariance, and this covariance statistic is element of range minus infinity plus infinity, yes, and the sign, yes, the sign minus or plus, yes, correspond with the direction of the dependence, yes. If the sign is plus, yes, if the sign is plus, like in our case, like in our situation, there is a positive, yes, positive dependence. We don't know the strength, yes, but only the sign, yes, either positive or negative direction, yes, of the dependence. So, according to numerator, we know that there will be positive dependence. And according to correlation coefficient, we know the strength of the correlation. Yes? So, this is the correlation coefficient, and now we will continue with the regression line and the calculation of intercept and the slope. So, first, what we need to know what is the regression line. Yes? We can write y is equal to b0 plus b1x. Yes? So this is the formula for the line where we have here dependent variable y, which is in our situation, in our case, monthly expenditures. Yes, that was written that we would like to try explain expenditures by number of members. Yes, so in our situation, this is dependent variable. B0 is intercept and B1 is slope of the regression line. So you can check, for example, this simple chart. Yes. There will be variable y and there will be variable x. Nobody in the household, one person in the household, 2 persons, 3 persons, 4 persons, 5 persons, 6 persons. Yes, and we have a data set. Yes, observations. 6,000 Norwegian crowns, 8,000 Norwegian crowns, 12,000 Norwegian crowns, etc. Yeah? So increasing development, and there will be some line, yes, with B0 like intercept and slope. And the slope. This one, yes, B1, yes, intercept and the slope. If you check your formulas, yes, I will check my formulas here, I can rewrite the formula for calculation of B1. It's necessary to start with B1. And in numerator, you can find the thing which you already seen. There is xy squared minus x squared times y squared. So what is it in the statistical language? This is covariance. Yeah? So again, we have a covariance in a numerator, and in denominator there is a difference between x squared mean minus x with stripe squared. There is a variance of variable x. Variance of variable x, yes? And after we have calculated b1, we can calculate b0, yes? Because in the formula of b0 there is used parameter, there is used the coefficient, yes? b1. So what's written on the table? y mean minus b1 x mean, yes? I will check it. Yes, it's all right. So these two formulas we can solve now, yes? I think that it's not necessary to have here this data set anymore. So I will delete these columns and I will leave here only the final results, yes, and we calculate B1. So again, in numerator there is a covariance. 61 minus 3.5 times 14.33. This is numerator, and in denominator we have x squared mean 15.17 minus 3.5 squared, yes, 3.5 squared, yes. So B1 is equal to, in the numerator we have the covariance. I have this covariance calculated here, 10.845. If you have positive sign, positive covariance in the numerator, you know that there will be positive dependence, yes? Positive dependence, and the line, yes, will be increasing. You will see increasing line. With positive covariance, you will see increasing regression line, yes? If the covariance is negative, yes, there will be decreasing line, yes? But in our situation, increasing, yes? So that's all what we need to know. I can delete this picture because we need a space, and in denominator there is a variance of variable x, yes? You can check the formulas that we have here, covariance divided by variance as x squared, yes? And this variance 15.17 minus 3.5 squared is 2.92. Very important for you, yes? Remember, covariance can be positive, negative, or zero, yes? But variance, the denominator, is non-negative value every time, yes? There can be zero, but mainly you can see here positive value, yes? Never negative, never, yes? Because there is a variance. So, 10.845 divided by 2.92, and the result is 3.714. So this is calculated slope of the regression line, yes? The slope of the regression line. Perfect. We can continue with calculation of intercept, with calculation of B0. According to this formula, we can select this data 14.33 minus this slope 3.714 times x, yes, variable x mean 3.5. Okay, 14.33 minus this result times 3.5, enter. 1.331, and this is intercept. So we have calculated intercept and the slope of this regression line, and finally it's necessary to write the regression function, yes, and interpret the coefficient, yes, interpret the value of regression coefficient. So I will start with the line. So y is equal to intercept 1.331 plus 3.714x. Yes, this is the formula of the line, and we know that the data set, yes, data set was given in thousands Norwegian crowns, yes, in thousands Norwegian crowns. So we know that this intercept is 1,331 Norwegian crowns, and the slope is 3,714 Norwegian crowns, yes. And finally, the interpretation. So there is variable x, there is variable y, yes, and there is our line. This is my line, yes, y is equal to 1.331 plus 3.714x. Yes, this is our line. And now, imagine that we have 0 persons, yes, in the household, yes. Nobody. X is 0. So result of this line is just intercept, yes? 1,331 Norwegian crowns. 1,331 Norwegian crowns, yes? This is the intercept. And 1 person, 2 persons, 3 persons, 4 persons, 5 persons, etc. With every other person in the household, yes, you need to have more money on expenditures, more by 3,714 Norwegian crowns. So this is the slope of this regression line, yes. If the house is empty, you still need to pay, yes, you still need to pay some autonomous expenditures, which must be paid for the household, even if the household is empty, without persons, yes. For example, internet connection, rubbish, yes, the cleaning of stairs, etc., cleaning of elevator, yes, etc. So autonomous expenditures, which you, like the owner of the household, must pay, yes, even if the house is empty. Household is empty. And with every other person in your household, you need to have more money, more by 3,714 Norwegian crowns, yes. Your grandmother arrived for 1 month, you need other 3,714 Norwegian crowns. Your uncle arrived to your house for 1 month, you need other money, other 3,714, etc., etc. So this is average increase with every other person in your house. According to this model, yes, according to this regression line, calculated regression line, we would like to calculate the value, the model value, yes, of consumption of expenditures of household with 4 members, yes. So you can see that we have here the data set. But we will use this model and we will try to calculate this value. So, y for the situation of 4 persons in the house, yes, is equal to intercept 1.331 plus slope 3.714 times 4 persons, yes, 4, because we would like to calculate we would like to calculate expenditures for a case of 4 persons, yes. So y4 is equal to, and we'll use the calculator, 1.331 plus 3.714 times 4, and the result is 16.187. Yes, so this is the calculation on the basis of our model. What it means 16,187 Norwegian crowns. Yes, and we can compare this calculation with empirical data, and you can see that we have here 15,000, and the estimate is 16,187. Yes, so you can see that there is a difference. Yes? There is a difference, and I don't know if this difference is a lot or it's not a lot. Yes. I don't know, 1,187 Norwegian crowns, a lot of money, yes, but in statistical way, we don't know if this difference, yes, is a lot or it's not a lot, yes, if this is significant or not significant, yes. So we must calculate some coefficient for evaluation of the model, and in your formulas you can find coefficient or index of determination r squared. Yes, coefficient of determination r squared. So we will calculate this r squared. For the calculation of r squared, according to your formulas, you need to know 2 sums of squares. Yes? So, sum of squares regression, yes, sum of squares regression divided by sum of squares total. Yes, so this is from your formulas, and we know that sum of squares total is equal to sum of squares regression, yes, plus, and I will check what we have here, error. Yes, sum of squares error, sum of squares error. Okay, so this we know, yes. So we need to use the formulas for the calculation sum of squares regression and sum of squares total. Calculate these squares and after calculate this ratio. Yes? So we will start sum of squares regression is equal to, I have here opened the formulas. So I can see that there is a ratio, no ratio, the difference, summation of squared differences, summation through all E, and we have here ye estimate minus minus the total mean of a variable y. Yes, I will check if this is correctly. Yes, this is regression sum of squares. So we need to calculate 6 estimates, as here, according to our model. 6 calculated values on the basis of the model, yes. And we know that this mean y with stripe was equal 14.33, yes? Am I right? I hope that it's correctly. So, we need to fit the data, yes? We need to fit the data, y estimate, yes? And we will calculate these values using this function, yes? 1.331 plus 3.714 times 1. 1.331 plus 3.714 times 2. 1.331 plus 3.714 times 3, etc., etc. Yes, so we will calculate 6 values. Yes, 1.331 plus 3.714 times 1. 5.05. I will use only 2 decimals. Yes, sorry for this. 1.331 plus 3.714 times 2. 8.76. 8.76. 1.331 plus 3.714 times 3. 12.47. 12.47. There will be 16 point something, yes, 1.331 plus 3.714 times 4, 16.19, 16.19, 1.331 plus 3.714 times 5, 19, 19.90, and finally 1.331 plus 3.714 times 6, 23.62, 23.62. Yes, I will delete this because we don't need this function for this time. Yes, and we have here the calculated values. Yes, and on the basis of this formula, we must calculate the squared differences. Squared differences between these values and the mean from dependent variable. Yes, so there will be y estimate minus y with stripe squared. Yes. Okay, so 5.05 minus 14.33 squared. 8.76 minus 14.33 squared. 12.47 minus 14.33 squared. 16.19 minus 14.33 squared. 19.90 minus 14.33, and this is in squares. 23.62 minus 14.33, and this is in squares. Yes? Okay, so I don't need this formula anymore. I will delete also this. Yes, and I will calculate these squares. Yes, so equal signs, and now 5.05 minus 14.33 squared. 86.12. 86.12. 8.76 minus 14.33 squared. 31.02. 02, yes. 12.47 minus 14.33 squared. 3.46. 16.19 minus 14.33 squared. 3.46. 19.90 minus 14.33 squared. 31.02 and 23.62 minus 14.33 squared. 86.30. 86.30. Okay, this is almost the end. If we calculate the summation through all E, we have here sum of squares regression. Yes, regression sum of squares. 86.12 plus 31.02 plus 3.46 plus 3.46 plus 31.02 plus 86.30. 241.38. Who using Excel, yes, who using Excel can see that these values are mirroring here, yes. This is different from this because of my decimals, yes. I used small number of decimal position, so I have here the difference, but if you use Excel now, you have correct values, yes, and these values are mirroring on this side, yes, because these values are centralized around mean, centralized around this mean, yes. So this is just a notice, yes. Okay, so regression sum of squares 241.38, yes. I will write it here because we will need this later. And what now? We need to calculate sum of squares total, yes, total sum of squares. So I will check the formulas, and total sum of squares is calculated like summation through all E, summation of squared differences between YE and Y mean. So not calculated values, but original values of the dependent variable, yes. So we need to have here more space, so I will delete this. You can write it next to the next columns, yes, to your papers if you have a space. I don't have space, and it's necessary to calculate here YE minus Y with stripe squared, yes, and here we can write 6 minus 14.33 squared, 8 minus 14.33 squared, 12 minus 14.33 squared, 15 minus 14.33 squared, 22 minus 14.33 squared, and 23 minus 14.33 squared, yes. So we will calculate 6 values here, yes, and I will start 6 minus 14.33 squared, 69.39, 69.39, yes. Okay, we can continue 8 minus 14.33 squared, 40.07, 40.07. 12 minus 14.33 squared, 5.43, 5.43. 15 minus 14.33 squared is 0.45, 0.45. 22 minus 14.33 squared is 58.83, 58.83. 23 minus 14.33 squared, 75.17, 75.17. Okay, so another 6 values. And here, when we calculate the summation through all E, yes, the sum of through all E of these values, we will receive sum of squares, total sum of squares. So 69.39 plus 40.07 plus 5.43 plus 0.45 plus 58.83 plus 75.17. So the summation is 249.34. Yes? So here I will write 249.34. Yes? So this is another very important result. If you remember, I said a few minutes ago that sum of squares total is calculated like summation sum of squares regression and sum of squares error. Yes? So again, like in the case of ANOVA, analysis of variance method, which I already showed to you, I will calculate for you the proof that we calculated these sum of squares correctly. Yes, I will calculate sum of squares error, like a difference between sum of squares total and sum of squares regression. Yes. So please, you can calculate the difference. 249.34 minus 241.38. Yes. So this will be calculated now. I will write the result here, sum of square error, and I will calculate here a proof, like a bonus. Yes? So 249.34 minus 241.38. Result is 7.96. We know that we are not able to reach the same value, but it must be similar at least. Yes, similar result. So again, I will delete this column because I need a space. Yes, and like a bonus for you, I will calculate error sum of squares. A training. Yes. So sum of squares error is calculated like summation through all E, and there is a difference ye and ye hat, yes, in squares. So we have here squared difference between empirical values, observed values, and calculated values on the basis of your function, yes, of the regression line. So here I will write ye minus ye hat squared, yes, and we will calculate these square differences. So here I will write 6 minus 5.05 squared. 8 minus 8.76 squared. 12 minus 12.47 squared. 15 minus 16.19 squared. 22 minus 19.90 squared. 23 minus 23.62 squared. First value, second value, third value, fourth value, fifth value, sixth value, yes? So we can do this. 6 minus 5.05 squared. 0.90. 0.90. 8 minus 8.76 squared. 0.58. 0.58. 12 minus 12.47 squared. 0.22. 0.22. 15 minus 16.19 squared. 1.42. 22 minus 19.90 squared. 4.41, and finally 23 minus 23.62 squared. 0.38. 0.38. Okay, it's possible to calculate here summation, the sum through all E, yes, 0.90 plus 0.58 plus 0.22 plus 1.42 plus 4.41 plus 0.38. 7.91, yes? So you can see that we have here small difference, yes, small difference between this value and this value, but this is only because of decimals, yes, because of small decimal position, so everything is all right. We have correctly calculated sum of squares, yes, and we can solve the final statistic, the final one for which we need, yes, to have everything here, these squares. So index of determination, yes, index of determination, coefficient of determination, r squared. So this is not necessary. R squared is calculated like sum of squares regression divided by sum of squares total. So in numerator 241.38 divided by 249.34. This r squared is 241.38, 249.34, 0.9681, 9681. So this is r squared. You must know that r squared is from range 0 and 1, and it's a ratio of explained regression, explained theoretical sum of squares on the total sum of squares, yes? If this value in numerator is the same like the value in denominator, yes, everything, all data set, everything is explained by this line, by this model, yes, by this function. Sum of squares residual will be therefore 0, yes, because we will have 0 differences, no differences between empirical values and fitted values, yes, but we have sum of square error, small, yes? So this r square is not 1, yes? But it's close to 1. So we can see that a lot of variability in the data, yes, is explained by our regression model. So I think that according to this r squared, our model is good. We have here another example, yes, 5.2. As you already seen, we spend about 50 minutes, yes, with solving a very easy example, very easy regression model, but I wanted to learn you how to solve everything manually, yes, because it's important. And now, because we have here practically the same example, but with different numbers, yes, there we have two different variables, price of house, yes, and the costs on maintenance of these houses, yes, so another two variables. And we would like to calculate regression line, yes? But if you see, we have here the values, higher values with decimals. So manually, it will be complicated, yes, to solve this. So in the table below, there are written the annual costs on the maintenance in thousands of Norwegian crowns and the price of the house in millions of Norwegian crowns, yes? And we would like to describe the dependence of costs on the price by the regression line, yes? So we can expect, yes, if you have a small house, yes, if you have small house which was cheap, yes, cheap house, small house with a small number of windows, small number of doors, only one floor, without stairs, without elevator, etc. Yes, with small land, you need to pay less money on the maintenance of this small house. Yes, but if you have a large house with 10 flats, yes, 4 floors, stairs, elevator, a lot of windows, a lot of doors, yes, etc. You need to have more money for the maintenance, yes. So we can expect that if the house is higher, yes, you need to have more money for the maintenance, and higher house and larger house, yes, with a lot of issues and equipment, yes, you need to have more money for maintenance. So we have here two variables, yes, dependent variable y, costs, yes, costs on maintenance, and independent variable the price, yeah, the price of the house. If the price is higher, yes, we can expect that you will need more money on maintenance, yes. So our duty is to explain maintenance, the cost on maintenance, yes. Describe the dependence of cost on the price by the regression line, yes. Okay, so there you have written variable y, you have written variable x, yes. And we will try to calculate B0 and B1 in Microsoft Excel. So, if you have English version of Excel, I don't know how this is, for example, different in your native languages, yes. But in Excel, if you click on data leaf, yes, you can see data leaf. We don't have installed a special add-in, yes, which will be placed in the right top corner, yes, of this screen. So we will install this add-in. So please click on File button, and find here Options. Yes, here on the last position we have options. Okay, you will see this large table where we have add-ins. Yes, here you can see add-ins. So please select add-ins, and here on the bottom you have you can manage Excel add-ins, and there is Go button with 3 dots. So please click on this Go button with 3 dots and select from this small table. Select Analysis Toolpath. Analysis Toolpath will be selected, click on OK, and in the right top corner you will see add-in data analysis, yes, for the data analysis toolpath. So, OK, and you can see now we have data analysis tools. So please select this data analysis tools. You can see that it spent some time, and it's necessary to find here function analysis tools regression. Yes, and you will see that this tool will solve everything what we calculated before 50 minutes. So everything will be calculated within a second. Yes, so regression. Okay. And you can see that there is a table with input y range, input x range. Yes, so our deal is written here. Yes, we have a deal that y is the cost on maintenance. Yes, our costs on maintenance, and variable x will be the price of the house. Yes, so we have this deal. It's written here in this example that we would like to try to explain this. So we will use this data set and we will put these data here. Yes, so it's very easy. You can select this column. Yes, and here you can select this column. Yes, we just selected these 2 columns. Yes, input y range, input x range. I did not select the labels, yes, so I will not select here the labels because I selected only the data set, and I think that that's all, yes. Click on OK, we will launch the least squares method, yes, and this least squares method will provide to you coefficients of the regression line. Yes? So I will click on OK, and you will see this new Excel sheet. So please, I will change the size of the columns. Yes, and I will delete what is not necessary. What is not necessary for you now, and it will be good to use only, for example, 2 decimals. Yes. So there is the table, and there are 3 tables. Yes, 3 tables. But the most important for us now is this one on the bottom. Yes. You have here Intercept and x variable 1. Yes, we have beta or B0 coefficient of B0, coefficient of Intercept, and the coefficient of slope of the regression line. Yes, so it's easy to rewrite these 2 coefficients on the whiteboard. Yes, these 2 coefficients can be rewritten on the whiteboard. Yes. Okay, so I will do this later. What else we had to do according to our example? Yes? So I will check the sheet 1. Yes, and I will check what's written here. Describe the dependence of cost on the price by the regression line. So I have calculated the coefficients. So I will write these coefficients on the whiteboard. Yes. Assess the quality of the model by the coefficient of determination. coefficient of determination r squared. Yes, we have here this sheet 2 with statistics, calculated statistics of the regression model, so we can check if there is, for example, here. Yes, you can see that r squared is calculated here in the case of regression statistics. Yes, so this r squared, like ratio, yes, ratio of regression sum of squares and total sum of squares, yes, is equal to 0.9704. Yes, 0.9704. You know that r square is in range 0 and 1. Yes, and if the r square is close to 1, yes, a lot of variability in the data set is explained by the model. Yeah? So this is close to 1, so probably this model is good. Yes. So this we find here in Excel, and what else? Determine what average increase of the annual costs corresponds, according to this model, to increasing of price by 1 million Norwegian crowns, and calculate the amount of the costs when the price of the house is 80 million. So we need to use whiteboard, yes, and we will finish this C and D. So our model, yes, y is equal to b0 plus b1x. This is our regression line, and we know that the variable y are costs on maintenance, yes, costs on maintenance, and variable x is price of the house, yes, and according to regression analysis in Microsoft Excel, we can write that the costs are equal to b0 minus 161 minus 161.68 plus 7.58x. So this is the line. And now our two questions. Yes, so one more time I will check these questions. Determine what average increase of the annual cost corresponds according to this model, increasing of price by 1 million Norwegian crowns. It's necessary to note that costs are in thousands. Yes, costs are in thousands, and price of the house is in millions. Yes, in millions. Okay, so increase the price by 1 million Norwegian crowns. So what it means, 7.58 times 1. 1 more million. Yes, so this increasing, yes, will increase these costs in thousands. Yes. So what it means? It means that if the if the price of the house is higher by 1 million, 1 times this coefficient, yes, the costs are higher by 7,580. In our situation, Norwegian crowns. Yes, so this is increasing of costs in real values. Yes, so that's easy. Just 1 times this coefficient, and increasing is moved here. Okay, and the D, calculate the amount of costs when the price of the house is 80 millions. Price of house is 80 millions. Yes, so y for the situation of 80 millions house is equal to minus 161.68 plus 7.58 times 80 millions. Yes? So I need to use the calculator here. Minus 161.68 plus, and this multiplication 7.58 times 80. The result is y80 is equal to 444.72. Yes, this is the result, but we must interpret this result. This is in millions, this is in thousand. So in thousands Norwegian crowns, this is 444,720 Norwegian crowns. Yes, so this is the final interpretation. Yes, 444,700 Norwegian crowns you need for the maintenance if you have house. Yes, which price is 80 millions Norwegian crowns. Yes, so we used this model for calculation of this value. Okay, we calculated two examples with regression line. Yes, if you remember, regression line y is equal to b0 plus b1x. This was our model, and we expected, yes, we expected that there was variable x, there was variable y, and for example, in the case of positive dependence, yes, we expected this shape of this regression line, yes, b0 and b1. But we can imagine a different situation. We can imagine, for example, this chart and this dependence. There is x and there is y. Yes, and you can see, for example, these values, these observations. Yes. And you can see that it will not be probably to use the line because of the shape of this observation, but maybe it will be better to use some quadratic regression function, the regression parabola, yes, because of the shape of the data set. How looks the regression parabola in your formulas? Y is equal to b0 plus b1x plus b2x squared. Yes. So for the calculation of regression parabola, yes. So for the fitting of these values, yes, it's necessary to have the variable x and variable x in squares. Yes, and after we will use least squares method, and we will calculate three coefficients: b0, b1, and b2. Yes, I know how to solve this manually. Yes, I know it. But in your seminar, in this course, you don't have formulas for the calculation this manually, so we must use Excel only. Yes, it's possible to do it manually, but you don't know it. Yes, you don't know how. So we will use Excel. Yes, we will use in Microsoft Excel variable y, variable x, and variable x squared. Yes, these two variables. We will use analysis toolpath, and we will calculate these three coefficients. Yes, and we will see what can we do with this. Yes? So the next example, 5.3. As I already said, we have here another example. It was analyze the amount of yield in dependence on the amount of used fertilizers. The data set is written in the table below. So what is here the most important? We can expect that if you have a land, yes, and if you want to have a yield, yes, it's necessary to use some fertilizers, yes, some additives. And if you use a little bit more fertilizer, you can expect in the short-term period that you will have more yield. Yes? So we'll try to describe this dependence. So we have here variable amount of fertilizer in kilograms, yes, in kilograms of used fertilizer, and amount of yield in cubic meter, yes, cubic meter. So data set is here, and we would like to fit the data by a quadratic regression function, the parabola. Yes, I show to you parabola here on the whiteboard. So fit the data by parabola and compare the results with regression line. How can we compare two models between them? We used for evaluation R squared, yes, but if we have a different number of coefficients in the model, Mr. Hellman said to you that it's necessary to use adjusted version of coefficient of determination, adjusted R squared, yes. So we will calculate two models, regression parabola and regression line, yes, and we will compare these two models on the basis of adjusted coefficient of determination, yes, and also we will characterize the tightness of dependence by appropriate index, by appropriate coefficient. This is the same like A, yes, we will fit the data and we will compare two models, and on the basis of these statistics, adjusted R squares, yes, we will interpret the dependence and we will evaluate these two models. So the data, yes, in columns are written here. Yes, you can see variable y, amount of yield. Yes, this is our dependent variable. Yes, our dependent variable. Independent variable, variable x, is amount of used fertilizer. Yes, amount of fertilizer in kilograms. So we already installed at in, which is hidden on the data leaf. Yes, but before we will use this special add-in, we must calculate here the second power of variable x. Yes, x squared. New column will be here. I will create here another variable x squared, yes? So there will be variable x squared, and you can calculate this variable like simple multiplication, yes, of variable x. So variable x times variable x one more time, yes, and you will reach the second power, yes, of this independent variable. So please do this, calculate this multiplication. And now you have here one more column, yes, and if you click on data leaf, yes, you will find here in the right top corner data analysis. Yes, so please select data analysis and find here regression. Yes, so data analysis, regression, and OK. And we have here this table one more time. I deleted the values, yes, the formulas which was written here from the previous example, and now everything is empty, yes? So, input y range and input x range. Y range is every time only this one column, yes? One column. And input x range, in the case of parabola, quadratic regression, are these two columns, x and x2, yes? So please select the data set, and everything else is the same. We will use new worksheet, we'll click on OK, and least squares method will calculate the coefficients for you. So I will select input y range, these values, yes? 1, 2, 3, 4, 5, 6, 7 values. Input x range, these 14 values, yes? Because we have here column 1 and column 2. Everything is alright, I hope. So click on OK and you will see the coefficients, yes? So OK, and I will zoom this document, okay, and I will use only, for example, 2 decimals, yes, and I will delete what is not necessary. Coefficients, home button, I will decrease decimals, okay, so this will be necessary for us. Yes, and I will name this sheet like parabola. Yes, so we have here a sheet with parabola. Coefficients for regression parabola are here. I hope that you reach the same values. Yes, and now I will try to reach the values of coefficients for a line. Yes, so please return back to sheet 1. And here we will again click on data leaf and data analysis. Yes, and again we will select regression and we will calculate coefficients for line. So we will select input y range, this variable y, and input x range, only this one column. Yes, it will be very easy. So please do this. Regression, okay, yes. Input y range can be the same, yes, but you must delete input x range and select this one column only. So please do this. This one column only, and you can click on OK, yes. And again, I will zoom this table, these tables, and I will use only 2 decimals in the case of coefficients. Yes, and I will use yellow color. So this is the most important for us now. So there is parabola and there we have line. Yes, this is parabola, there we have line. Okay, so it will be good to rewrite these coefficients, these values, these formulas for line and parabola on the whiteboard, but before this I will also find classical R square, yes, classical R square for the case of the line. Yes, so there you can find classical R square for the line, and here we can find classical R square for regression parabola. Yes, and these statistics will be also rewritten on the whiteboard. Yes. Okay, so I rewrite the coefficients of regression line and coefficients of regression parabola from Excel on the whiteboard. Yes, so if you remember the yellow values, yes, the regression line is equal to minus 53.88 plus 15.4x. Yes, so this is the line. And the regression parabola is equal to minus 32.22 plus 7.3x plus 0.72x squared. Yes, so we have here our models, two models, and I rewrite it r squared, classical r squared of regression line and regression parabola. Yes, and now if we use this classical r squared for evaluation of the model, we could say that parabola is better one. Yes, parabola is better. But Mr. Hellman said to you, and this is also written in the textbook and your presentation, that if we compare the models where we have different number of coefficients, we must use adjusted version of r squared. Yes, adjusted version of r squared. This adjusted r squared can be calculated according to formula which is written in your formula sheet. There is 1 minus classical r squared multiplication, and there is a ratio n minus 1, and there n minus p. N is number of observation, as we have n equal to 7 observations. You can check the number of lines. Yes, 7 observation, and p is number of parameters, number of coefficients. So here you have 2 coefficients. Here you have 3 coefficients. Yes, so I will calculate this adjusted r squared for case of parabola. So adjusted r squared is equal to 1 minus this classical r squared 0.8687. Yes, and there will be multiplication and in numerator. Yes, in numerator we have 7 minus 1, and in denominator we have 7 minus 3, because number of coefficients is equal to 3. So please calculate here adjusted r squared. Okay, so 7 minus 1 is 6. 6 divided by 4. Yes, 6 divided by 4 times, and there is 1 minus 0.8687 and 1 minus this result. So result should be 0.80305. Yes, so this should be adjusted r squared, adjusted by number of coefficients, yes, for the case of parabola, and adjusted r square for line we'll try to find in Microsoft Excel sheet. Yes, so I will use again Microsoft Excel, and we will try to find these adjusted r squared here. Okay, so can you see this window? This is the parabola. Yes. And from parabola we rewrite it r squared on the whiteboard, and below this r squared is calculated adjusted value of r squared. So if I use only, I don't know, 5 decimal positions, you can see that I reached almost the same value on the whiteboard. Yes, I used only small number of decimals. Yes, so this is the reason why we have here the difference. But on the basis of this adjusted R squared, we are able to compare the models. Yes, so parabola has only 80%, and the line which is written here, again I will use only for example 5 decimals. The line has more. Yes, 83.6% of explained variability. So I can write here this value 0.83625. 83625. Yes, you can see this value 0.83625 is higher than value 0.80305. So the regression line in this situation is better model. Our last duty is to calculation according to better model, yes, the amount of yield when 8 kilograms of the fertilizer was used. Yes, so calculation of amount of yield in the case that you will use 8 kilograms. On the basis of adjusted R squared, we selected regression line. So we will not use regression parabola, we will use regression line, and according to regression line, we will calculate this amount of yield. And this will be the last thing which we will do today. So there is my line, yes, regression line, and I would like to use 8 kilograms of fertilizer. So the amount of yield when we use 8 kilograms of fertilizer is equal to minus 53.88 plus 15.4 times 8 kilograms. Yes, so on the calculator we can calculate 15.4 times 8 minus 53.88. Okay, so the result is 69.32 cubic meters of yield. Yes, if you use 8 kilograms of fertilizer, you can expect that you will have 69.32 cubic meters of yield. Yes, so this is the end for today. I hope that everything was clear. Remember, if we compare different models with different number of coefficients, we must use adjusted version of R squared. Yeah? So this is the most important now. So that's absolutely all. This is the end of our 5th seminar. Yes, and I hope that I will see you next week. So have a nice day and bye bye.